Okay, so thanks a lot, and good afternoon, everyone. So it's a really pleasure for me to give this talk today about some work we did with my former PhD advisor, Christian Hagendorf, which will be about bipartite fidelity in the XXZ Spin Chain. So for those of you who know me, you know that there are two things that I love in life. So the first thing is taking funny pictures of Nicolas and Eric with a nice sunlight in the background. And the second thing are outlines. So the outline of the talk is pretty simple. I will first tell you about entanglement and bipartite fidelity, and then I will define, well, the system we considered, and then I will give you the results, right? It's pretty standard line of event. So let us begin with quantum entanglement. So actually, it's a very nice, timing, because today the Nobel Prize in Physics was announced and was not given to this gentleman, but actually to Alain Aspect and other people who contributed to actually show that quantum entanglement is not a mistake in quantum mechanics and is actually a genuine, quantum phenomenon that you can measure. And so it's a very nice timing, I think. But anyway, so historically it was discovered theoretically in a thought experiment by Einstein, Podolsky, and Rosen in what we know as the EPR paradox. Which goes as follows. So imagine you have two particles, two electrons, which are in a state. So in quantum mechanics, a quantum state is a vector in some Hilbert space. So here, imagine that you have one red electron and one blue one, and they are in the state which is a superposition of up, down, and down, up. So it's the spin 1/2 of the electron. And now imagine that you actually send these two electrons in two opposite directions across the universe, and that some observer A measures the spin of the first red electrons. So the laws of quantum mechanics tell you that if A observes spin up electrons, then she knows, or he knows, that B will see a down spin with 100% probability. But this happens independently of the physical separation and instantaneously. So there seems to be like a contradiction with the laws of relativity, which, I mean, in the end, there is not, of course, but that's why Einstein initially was a bit. And this is because of quantum entanglement. So the definition is the following. We say that two systems are entangled if measuring one influences the state of the other, or gives you information more precisely about the state of the other, independently from the physical separation. And so mathematically, a quantum state which describes two systems A and B, okay? So if you cannot write it as a product states for two, your two subsystems, then there is entanglement. And if it is a simple product, then there is no entanglement. It's kind of a binary. So here I told you about entanglement between two electrons or two spins, but actually a very, interesting, in my opinion, field of research is in studying entanglement, but in the context of many body systems. So here, A and B would no longer be one electron in the other, but actually a whole subsystem in a many-body system, right? So in that context, let's give you first some definitions. So the Hilbert space typically can be written as a product of local Hilbert spaces. So if you think of a spin chain, we'll have A and B are two parts of the chain, and you can have local states for each spin, which gives you HA and HB. And then if you have a system in the pure states using Schmidt decomposition, you can write this as a sum of products of local. So the psi A are the local basis for A, and this is a local basis for B. And so this is a product. And actually, the PI, you can choose them to be real and positive. So that's Schmidt decomposition. And now to actually study your system, a very convenient tool is the so-called density matrix, which is this projector on the state psi. So when psi is a pure state, it's kind of trivial and not really useful, but actually it becomes interesting when you want to study only physics, say in A. So if you only study observables that are defined in A, for example, then you use the so-called reduced density matrix, which is the trace over B of this total density matrix. Okay, so that's for like general definition, but then the question is, how far is psi from a product state, right? Because the definition of entanglement I gave you is actually a binary one. It's either a product state or it's not. But now the question is, if it's not a product state, then is it almost a product state, or is it like not at all, right? So we want to quantify this property. And the most general way to do so is through the Rayleigh entropies, which are defined as follows. So you have an index n, which is not necessarily an integer, but most often it's an integer. And so you compute this log of trace of rho to some power. And so if this is 0, it tells you that there is no entanglement. And if it's not 0, well, there is. And the most famous measure is, of course, the entanglement entropy, which is the limit n goes to 1 of this quantity, which is the von Neumann entropy of the reduced density matrix. Okay, so I won't tell you much more about that, but that's kind of a very broad, way to think about those things. Today, I want to tell you about another way of answering that question. Right. And that way is through the so-called bipartite fidelity. What is it? That's the definition. So that's actually the logarithmic bipartite fidelity, but we don't really care. So so the denominator here is just normalization. Let's forget about the log, and the main thing is this overlap here. So what you have on the right, so the ket on the right-hand side is actually the ground state, psi AB here. It's the ground state of some Hamiltonian H, which is a sum of Hamiltonians for A, B, and some interaction between the two. So it's really the Hamiltonian of the whole system, A and B, which interact. And on the left, what you have is a product of ground states for just A, and so HA and HB. So it's kind of comparing the ground state of the whole system with the system where you basically cut, like if you have a chain, you cut it in two parts and they don't interact anymore. So if your ground state is a product state, this overlap gives 1 and the log gives 0, and otherwise it grows. So this quantity has many interesting properties. So for example, it can detect critical regimes, so quantum phase transitions. When you are not at criticality, there is an area law, so it scales like the area of the boundary between A and B. And at criticality, it gives you insights in the underlying conformal field theory, which I will tell you a bit more just now. And so actually, these properties are in common with the entanglement entropy, which has been known for quite some time now. So I think that's one of the reasons why this quantity was also why Jérôme and Jean-Marie were interested in this quantity in the first place. Okay, so that's for the general definition. So now, before moving on to some calculation, I want to give you a small interlude, which will be useful actually about the connection we all know about 1D quantum mechanics and 2D statistical mechanics, because I think it's very nice to remember this. So in the context of 1D quantum mechanics, the picture is the one I just told you, right? So you have one chain and you cut it in two parts, and you want to compare these quantum systems. This has also an interpretation in terms of underlying two-dimensional statistical model. So in that case, what you have is, say, a lattice model, where you need to compute a partition function on such a lattice with some spans geometry, right? So you have the leg for A, leg for B, and then the whole system. So in the quantum language, it's just what I told you. You have the Hamiltonian, you compute the overlap of ground state of this Hamiltonian, and this gives you the bipartite fidelity. And in the static picture, actually, your main object is the transfer matrix, which can be thought of as the exponential of some Hamiltonian, some quantum Hamiltonian. And the equivalent of this overlap now becomes this partition function on this lattice. And the free energy in the large M limit gives you the bipartite fidelity. So now, one extra layer, actually, so when you have a 2D stat-mech model, which has some conformal invariance property, in the scaling limit, it can be described by a field theory which lives on this spans geometry. But now you insert fields, and it's described by this so-called CFT, so conformal field theory. And in that case, the main object you want to compute are correlation functions of fields inserted on the lattice. So if you don't know much about it, it's not a big deal. I mean, it's just, for those of you who know, it's a nice picture, but it's not the main points of today's talk. So don't worry too much. But okay, so that's kind of the general setting. And now let me give you the prediction in the context of CFT. So basically what Stéphan and Dubail did is that they computed the bipartite fidelity using only field theoretical arguments. So not from a lattice model, but actually directly from the field theory. And then the general idea is to then try to compute this quantity in the lattice and see if, you know, the large M limit from the lattice model gives you the CFT prediction. So in the case where all the fields on this span's lattice are primary fields, so the two-point function is this very general form where delta is the scaling dimension of the field. This is the prediction. So I will. So here n is the size of the. It was the size of the chain, but here you are of course in the large n limit. And so C is the central charge of the CFT, and the delta, they are the weight of. So delta 1 to 4 are the weight of all the fields you insert here. And actually, they enter in the definition of the function G1 and G2, but I didn't write them explicitly, but they enter here. Okay, so again, this is not explicitly written in the formula, but you have this aspect ratio, which is the size of the leg A as compared to the size of the whole system, which has to remain a constant in this scaling limit. And finally, okay, G1 and G2, they are universal in the sense that you can find an expression for these quantities in the CFT, framework up to some constant. But okay, so just remember now, it's just that in the CFT you can make calculation, and now we will go back to the lattice and see if we can recover this result. First, I will give you a slight state of the art about these bipartite fidelities. So, as I told you in the CFT, so in the case of rational CFTs, Stéphan and Dubail did the work for us, and then actually with alexis and Philippe Ruel, we generalized some of this calculation to the case of non-unitary logarithmic CFTs, and also to model with periodic boundary conditions. So in that case, your system is really a 3D path. You have the periodicity in each leg and the way. So this makes for pretty nice pictures for the talks. And on the lattice, what you have, so Stéphan and Dubail, that they had some result for the XX and XY spin chain. So in the infinite XXZ chain at delta bigger than 1, then Roberts actually derived also some results. And Hagendorf and Lienardi did it for the supersymmetric XXZ spin chain, which I will tell you about a bit later. Robert, you're here. I didn't find you. And finally, again, with Alexis, Philippe, and Jean, we did it for the critical dense polymers and XXZ spin chain with periodic boundary conditions. And every time you find the perfect agreement between the two. And finally, there are some conjectures for multi-partite fidelity, so where you have many legs, and not just two, but many legs, again by Lienardi and Hagendorf. Okay, so that's for the kind of the quantity of interest, but now let's focus on the system of interest, which is this XXZ spin chain at the combinatorial point. So the XXZ spin chain, I think at least most of us know what it is, right? So it's a sum of local products of polymatrices, which describe spins which interact on a chain. And here the model is so you consider an open chain, so not with periodic boundary condition, but open ones. And at each end of the chain, so in red here, you put a magnetic field. So it's not a global magnetic field, it's just local magnetic fields at the boundaries. And the combinatorial points refers to a very specific choice of the parameters. So delta is -1/2, and P and P bar, so the magnetic fields, they depend on some parameter X, which is some real parameter for the moment. And of course, I will try to tell you why this is called the combinatorial point in just a moment.
This is not the same as the free fermion point.
No. So in the free fermion, you get delta is 0. So this you could have one coefficient in front of the X and the Y component, but 0 Z component. And this you can solve by Jordan Wigner and then Boglio, the other name, transformation. And this you can solve exactly, but when you have a delta, it's no longer possible. So it's not a free Fermion model. No. Okay, this is actually an interest of this result, is that we get an exact formula for this bipartite fidelity for an interacting, so delta non-zero, an interacting model. It's one of the whole points. Okay, so what is this connection with combinatorics in just one slide, which is of course impossible. So a main result which was observed more than 20 years ago is that if you take the XXZ Hamiltonian with this delta equal minus 1/2, but now with periodic boundary conditions, so no boundary fields, and odd length actually is very important. Then I think at the beginning there was only numerical work. I think maybe I'm wrong, but that's what I have in mind. Actually, the ground states of the XXZ spin chain has a very special and simple eigenvalue, which is just -3/4 of the size of the chain. And so if you denote the ground state vector by this notation, and you normalize it that way, so of course this vector is the sum of local bases for each spin configuration. And so if you normalize this vector such that the configuration corresponding to small n spin down and n+1 spin up is 1, so it's very fine-tuned, but okay. Then what you get is that the largest component of this vector is exactly this an number, right? So a very simple product of ratios of factorial number, which if you've been paying attention last week to Sylvie's lecture, this number is actually exactly the number of n by n alternating sign matrices. So very important combinatorial object which appears somehow in the spin chain, which is a purely quantum integrable system. So yeah, so alternating sign matrices, I remind you, these are square matrices with entries 0, 1, and -1, which alternate and which sum on each row and column to 1. So 3 by 3 they are given here. And okay, so the next number was 42 indeed in the sequence. And okay, there is a very long story about this alternating sign matrices. It's really interesting, but okay, just to tell you, this is one connection between spin chains. But actually, it's a very long story, and there are many people who contributed to that field, and I could, of course, not tell you about it in half an hour. But okay, just to say it's kind of an interesting and active field of research, which combines, in my opinion, mathematical beauty and rigor. So that's always nice, I guess. And it allows us actually to make exact computation for an entanglement measure, which is also interesting.
Can you say a word about why it has to be an odd number of sides?
Actually, I think maybe correct me if I'm wrong, but I think that essentially this was just a numerical conjecture that they observed at the first. Maybe there is a deeper reason, but I'm not sure I could explain it now. But at the beginning it was just, I think, numerical trials, and they observed this only for the odd case. Okay, so now I am actually going to tell you a bit more about our result. So I remind you, so this is our model, and this is what we are going to do. So we will have a chain of length n and two systems of length na and nb that we kind of cut. And so I should say, so Hagendorf and Lienardi studied this Hamiltonian, and they show that it also has a very simple ground state eigenvalue. And actually, we use many of the results to kind of use properties of the ground states to make our calculations. So this is a very important paper for us.
And it's also only for odd volume or both?
I'm sorry?
Again, this only for odd volume or now?
No, I will tell you. For now, just follow me. But for now, n is just n, and then depending on the parity, I will give you.
Eigenvalue equation holds for any.
Okay, I'm sorry. I think it's for any. Okay, sorry. No, I think it's for any n. And what we want to compute is this quantity. So now I rewrote the bipartite fidelity in terms of this O function, which are basically the overlap I showed you before. Okay, just fancy we're writing it. And what we have, so let me give you the results because it's quite technical and again too long for a talk, but it's a theorem, so it's a rigorous result. So if you have NA and NB, and then small n is simply the floor function of the total size, then when NA and NB are even, actually so maybe I should spend more time. So really O is really this overlap, okay? So this O is actually, so I will tell you about the gamma just now, but essentially it's just one simple determinant which depends on x, so the parameter at the boundaries, and here are some binomial numbers. So it's kind of a very simple, simple formula. And in the case when one of the lengths is odd, you get a very similar formula. Okay, just slight differences, but very, very similar. And the gamma numbers are when n is so n, so the NA or NB, right? So it's not the total n, but when it's even, it's the number of alternating sign matrices with some symmetry. So it's a very, it's not every alternating sign matrices, but those with a special symmetry. But let's not get into too much details. And for odd n, it's a number. It's another number which with a very explicit formula in terms of factorials, which also counts partitions on the planes. So it's also another interesting combinatorial number. That's the result for finite size. So you take a chain, give the finite size, and this is the exact finite size result. Yes. So for x equal 1, we recover the results of the supersymmetric XXZ spin chain. So that's important. And so the derivation is quite technical, but it involves QKZ equations and many properties, as I said, we use from this paper where they actually studied the ground state eigenvalue, ground state vector of the XXZ spin chain and give many properties.
So could you recall what the supersymmetric chain is?
Well, so I guess an easy way would be to set x equal 1 here. So remove you remove the boundary fields. No, sorry, you don't remove them. You give them a very specific value, x equal 1, and this Hamiltonian, then you can show that it can be written as an anti-commutator of some nilpotent charges, and it has a supersymmetry. But it's really interesting, but I don't tell you much more now. But yeah, for x equal 1, you can write this Hamiltonian as a supersymmetric Hamiltonian in the sense, yes, that it's an anti-commutator of nilpotent charges.
So it's just the special case when x equals 1.
Yes. Yeah, and so the second result and the last results is the scaling limit. So now that we have a result in finite size, we want to take the limit where everything goes to, so all the sizes go to infinity, and see if we recover the result from CFT, which I showed you before. That's what we do. So here, this ratio NA over N remains fixed, and you send everything to infinity. And again, it's so the asymptotic is rigorous, and what you get is this expansion. So you have a log n term, then a constant term here, and then some non-universal factor here. And the same, almost the same when you have one of the length which is odd, just that this term is a bit different. So that's the result, where D is some explicit function which depends on R, and R depends on X. So everything is perfectly well controlled. And just, for the pleasure of the eye, so this is the match between the finite size and the asymptotic result for around 70 sites. So of course, this is not the proof, but still, it's always nice to have this kind of. And okay, as remarks, so we use some result from Gorin and Panova for the asymptotics of polynomials that we use in our proof. And yes, so this scaling limit, which I showed you, actually exactly match the one I showed you at the beginning of the talk. So this formula from Dubail and Stéphan, where C equal 1. So this is the known value of the central charge for the XXZ spin chain for delta smaller than 1 in absolute value. And all the weights are equal to 1 over 24. And in particular, this implies that this function here is exactly 0 in that case. So that's a very specific case. But this is exactly what we observe, because in the formula, we don't have any log n over n term. It's really, the next term is really over the 1 over n. So it's a perfect match. Okay, a thing to note is that the result is actually independent on x. So x was the field on the boundary depend on x, and so they don't change the universal properties of the chain. It's almost disappointing, I should say, but okay. In the end, we understood why is it the case, but okay.
Is there a similar log n expansion, large n expansion for the entanglement entropy?
Yeah, okay, so this is actually a good question. I should have mentioned that, yes, indeed, the entanglement entropy for, say, a critical spin chain also scales like something proportional to the central charge times log n. But the coefficient then, they are very different. But that's actually what I meant at the beginning of the talk, but I didn't write the formula. But this is what I meant by this gives you information about the underlying CFT, is that if you compute the bipartite fidelity and you have a log n divergence, then you could extract the central charge. And this is also true for the entanglement entropy. Okay, so actually it's already almost the end. So let me conclude. So in summary, the bipartite fidelity is related to quantum entanglements, which is related to Nobel Prize, so, in a way. So we could have exact results in finite size. In finite size, that's actually important. Right? Exact result in finite size for the open XXZ spin chain at the combinatorial point. And with a rigorous scaling limits, we could show that these results actually perfectly match the CFT predictions. And so there are many possible outlooks. One of them is to study, as I told you, the multipartite fidelity. So when you have many legs in your pants, I don't know, you could find funny names, I guess. On that. We could also study the XXZ spin chain at delta equal 1 minus 1/2, but with periodic boundary conditions, because this also has a combinatorial structure. But so probably that some of the results generalize, but it still has to be done. Okay, so still here, but of course, a question you should ask is, okay, but what about arbitrary delta, and can you do this with algebraic beta ansatz and Slavnov formula? So we've tried, we are still trying. It's hard, but who knows? Quantum separation of variables. So this I mentioned, for those of you who know, it's kind of another way of treating some integrable systems which have a natural separation, and some products arise. So one question is, could we treat bipartite fidelities in this setting? Maybe, but again, it would take some work to actually see if something is possible. So, and I finally just mentioned that actually overlaps similar to the ones I just described to you are relevant for the investigation of what we call symmetry resolved entanglements, which was in this paper also from Alexei, which is also something I care about. So, but again, all of these are to be investigated further. And with that, I thank you very much.
Thanks a lot for the talk. So we are on time, so maybe 1 or 2 brief questions.
Hi. So many of the results for XXZ delta is minus 1/2 also hold for the XYZ model along its combinatorial line, including exact results about ground state. So can you access that line for bipartite fidelity? Because that would give you access to non-critical models.
Yes. Okay. So again, that's something I think Christian wanted to look at, to study the non-critical. Yes, as you just said, actually, to try to generalize this. So I haven't. Maybe we should ask Christian if he has thought more about it. So I don't know, but I think it's certainly interesting to think about it. But probably it's going to be quite involved. I mean, all of this is already quite, at least for me, pretty technical. So I cannot imagine with theta function and stuff. Maybe it's doable.
Other questions?
I think there is one from John also. Oh, okay.
Yes, I wonder if you could just say a word about what you mean by symmetry resolved entanglement entropy.
Ooh, that's another. Okay, symmetry resolved in 1 minute is. Oh, but that's okay. So if you have a system with a global charge Q, which commutes with your Hamiltonian, then if you consider the reduced, so the matrix Q commutes with your Hamiltonian, and Q can be written as a sum of Q1 plus Q2, where 1 and 2 are your 2 subsystems. Then what you can show is that if you take the ground states and compute, say, the reduced density matrix for 1 subsystem, rho A, it will commute with Q1. So this implies that actually rho of A1, maybe I should call it rho A, but okay, has a block diagonal structure where basically each block should be diagonal. So this maybe each block corresponds to a given eigenvalue of the charge, but yeah, so it's really a block diagonal because of this commutation relation. And then what you do, so when you compute entanglement measures, right? Usually you do this minus trace of rho log rho. Okay, so this would be like the total entanglement of your system A1, A1 and A2, between A1 and A2. But what you could do is actually say, okay, instead of taking this whole matrix, I just want to take, the contribution from this block. And so here, replace rho of A1 by rho of A1 for some value of the charge. And this gives you what we call symmetry resolved entanglement measures. And you can show, for example, that the total entropy can be recovered as a sum over all the charge sectors of the probability to be in that charge sector times symmetry resolved entropy minus some entropy associated to the probability, so minus PQ log PQ. Okay, so there has been a lot of interest about this quantity because it gives you access to kind of a deeper understanding of how each sector contributes to the total entanglement. But again, if you want to know more, then you should come and we should discuss because it's a whole talk. So
In any
the
case-
Q, sorry, the Q is if you don't have a Hamiltonian, the Q, how is Q related to the state that you're considering?
okay, so Q is the eigenvalue of the total charge. So it's a particle number in the XX spin chain. And I think I cannot say much more now, but I could say more if you want.
But we are a bit over time, so I'm sorry, but I suggest we continue discussion somehow afterwards. So thanks a lot to the speaker.